Nothing much. So let me start. Okay, here it comes. Oops, I should not. I go to the. Today seeing lesson 6, which is on compatible and incompatible meshes. Not a big topic, but a quick understanding of what exactly these two mean or what's the difference. And let's move on with that. Let me open the file set as well. Let me open file set. Where is it? Lesson 5, lesson 6. Case studies. Rotor. This. Okay. Let me keep PDF also open so that I can use to show anything quickly. Excellent. Start compatible mesh, and the images over here should give a quick idea on what exactly they are. If you observe here, there is a kind of mesh continuity that is seen between these two parts. Whereas here, it is as if these two parts are meshed separately. There is no relation, and software will create a set of equations between those two surfaces to ensure a good or to ensure connectivity between those two parts. Um, over here, very simple: compatible solid element mesh with bonded contacts. As simple as, or if I put it in a different way, assuming these two parts are cutted into a single solid geometry, it is as if there are no two parts. There is some merging that has happened at those surfaces. Then those represent a compatible mesh. When case of incompatible, that is not the case. They remain separate. Meshing is done separately, and only connections are created later on internal to the software. So the option is present somewhere under component contacts or global contacts. You'll see it. You will see these two radio buttons at the bottom, which are not compatible and incompatible. And the image is showing you if a compatible mesh, then it will try to imprint a similar kind of mesh on second geometry, and the appropriate nodes will be merged. They will not be separate, but they will be merged. This is what is the biggest difference. In case of an incompatible mesh, it looks it looks bad, and excuse me, sorry. Yes, and there's some hiccup in the throat. Okay. Compatible, as seen here, it's completely distinct or separate. Apart, in the case of incompatible solid mesh, if it is selected, you will see this extra option called as more accurate, slower, right? Of course, in limited automatic software will decide simplified is the old way of doing it, and more accurate, slower is a kind of new algorithm. that was implement for incompatible solid mesh. Actually, on the face of it, it will not show you anything, but internal to the software, this is the kind of difference that is happening. So if you see this, let me check if I have a different image. Yeah, these two. Mhm. Old way of doing it, the image in front of in this web. The node. This is basically a node-based contact. Uh, it would obviously connect a single node to a particular node of element which is nearest to it. And obviously, you can imagine the solution time would be faster because lesser number of contact elements over there, equations, and other one, there was a bit of chance of inaccuracy. And this gap that you are seeing, let me take the pointer. Uh, this gap that you are seeing here, it is more. It would increase or decrease based on the quality of the mesh between these two. Quality in the sense, one of the part may be having a very fine mesh and the other may be having a very coarse mesh. Then obviously the connection should be lesser and lesser and things may be appropriate. Whereas new method, which is available now, it's more of a surface-based contact. Results at the contact interface are uniform, but solution time is longer. So it's trying to cover more elements, well connected, and obviously this would create a longer solution time. So quickly show this in this software. Here, this. Let me go option. First, to show you where the option is. So here, use options: compatible and incompatible, right? And in both cases, if you can give it created even between two surfaces which are a gap, and this is a kind of new feature that has come up. In the past, it used to be only surface to surface contact. Now, assuming it this one is the compatible thing, let me create mesh for this. Create, what happened? It's already there. No, sorry. Mesh. An exploded view for this. No, that's okay. I will try it. Let's see here. You can see the end nodes. There is a nice connectivity that is present. Hopefully, only the. Only let me show this. So created a kind of imprint of that mesh over here. Excuse me. So now, not I should say common sense, but if you observe this, would find it difficult to mesh big geometries, huge big geometries, which also has small parts which are sitting on it. In cases, obviously, it makes a bit hard, and we may not be able to simulate it. Rather, the words are incorrect. We may not be able to mesh it. The server may fail. So in such cases, especially huge assemblies, wherein there are parts of different sizes, a mesh might fail at certain locations or salts. In those cases, it is advisable to use incompatible mesh, and it will automatically mesh. These are cases wherein you will observe, if you try to mesh the parts separately, it meshes. When you take it to the assembly, it fails. And so in the assembly, if it is incompatible mesh, it mesh each of these parts separately as if there is no relation, and on and thereon it will create local connections at appropriate places. So quickly see this. If it is an incompatible mesh, what has been done or how it looks. On power saver, so it is a bit sluggish. Now it should be better. So clean, like if there is no relation between these two, however, the contact condition will ensure they are connected and the results will be there appropriately. Email on the training level. So, which you may not be visibly see it. If you want, and if you can manually select this option of more accurate, accept it and solve it, you might see a few differences in the results, especially at the local condition, but otherwise there is no big difference. Obviously, if you are looking at more accuracy, if you think different bonded conditions created with the incompatible mesh are not enough, you can use this option, and that should help you get it more accurate, right? Fine. I think this is what I can highlight on chapter. Any questions, guys? Let me just, if I missed out on any important topic, I'll just cover it. Stress singularity topic, which we discussed yesterday, kind of where you might be able to see, especially if it is an incompatible mesh, because separate and there is a kind of changes happening at the connection, and you might see those kind of behavior. But this is a case wherein you can safely neglect singularity. Okay. If no questions and if no specific things on that, okay, this one is a bit old. I don't think I can now. Yes, let me quickly open the appropriate chapter model from lesson 7. I think initially I have already introduced you to shell elements, and if you observe this, this is a classic example wherein the thickness is around 2 millimeters and is consistent throughout the geometry. It is same, right? So these cases or such a model is eligible to be treated as shell element. Now, when we create these shells, we do different options. Let me try to create a new similar study so that I can quickly show you from scratch. So this is solid geometry. Just use it in the example and just to show you a particular way. There is a surface geometry that is already created over here. So you can either use the mid-surface creation option in SolidWorks to create, or just offset some surface and have that geometry. So this is a case wherein we wherein a solid entity was there and surface geometry has been added later on, as, just to show you in this particular example. So if I go in over here, typically obviously we are getting these two geometries. At the moment I suppress or exclude this from analysis. So we have only this one. So this one, when if I have to treat it as a shell, I have few different options, and one of them is define shell by selected face. Option will see what exactly would be the difference in thin and thick. In short, we already discussed it. But say if I select thin, I select it, probably, or typically I would end up selecting the applied surfaces of the solid geometry. Okay, this is what is happening. Then, I do have the option of viewing it. That is, if I select this particular surface, if I give a thickness of 1 millimeter, actually in this case it should be 2 millimeters. Where exactly or how would be the internal to the software? So this is not visualization; it is more for calculation. So obviously you can see if I select it, it is going outside. It does not make any sense. I like to have it appropriately. I can go here, offset. You just try the different options, but basically what we need is the so first of all, what was selected by default is the mid surface. So the surface that we had selected is the mid surface, and the calculation might happen something like this. That is, halfway through the geometry it is done. Whereas take the top surface, it gets more worse. The surface looks nice. You can see that. This is the kind of that I want, so that it would be accurate. And just to show you, there is one more option called as specification. It may rarely used, but could be a case wherein the selected surface is actually offset or away from the actual geometry. These are relevant, especially in those cases wherein there are gaps created intentionally or because of the modeling conditions, either probably creating a edge where or certain surfaces there, whereas the other part is a solid, and when you come across those geometries, you'll automatically understand that this is more relevant option. In this case, it is obvious we are selecting the bottom surface that is represented geometry appropriately, and of course we have the thick and thin option. I'll just quickly go through the PDF that has that's then what exactly it means, and I think yes, only composites I'm not covering here, but of course you can always explore it. Select composites and this select when the same, but a few more different settings which will come into picture here. We do the simulation premium training, we'll be doing the composite part of it. Okay, so let me stick to thin and thick. This is, by the way, this is one way of creating a shell element. If I quickly mesh this, it's something like this. So with condition, if you remember in the first class we discussed orange means certain part of the surface. Here is the bottom surface. We can the colors, etc. Right? So this is one. Second one could be a bit other one wherein you already have a surface, no big deal. Let me get rid of this part and I directly mesh this surface geometry. Okay, error. Yeah, I got it. So the thing that you need to give over here is the thickness of this particular surface geometry. No location, assuming that I taken care when you did the CAD geometry, right? So this is it, and accept it. I'm over here. If you'll also see this option called as flip shell top and bottom. Right? See the orange color on the screen, it is flipping. Frankly, or other way, or the way of saying it, if there's only one surface or if there is only one set shell element, then this may not affect much. But there are multiple surfaces or multiple shell elements, definitely it will affect, and you might see addition of stresses incorrectly when at the connections as well as throughout the geometry. So it may not affect displacement, but for stresses it will make a big difference. So ensure that after the meshing is done, all bottom surfaces remain at the bottom. Orange color is uniform throughout the geometry, and other way around, that is the gray part of it. So this is a very important thing. If especially in large geometry, you need to take care of this properly. Let me see this. Right. So this is how. Okay. I think we may not discuss or have an example in this topic. Let me check if the other model that I opened has it. Yes, I think so. Okay. My point of highlight was this: if I create a new study for such geometry, which is made of shell parts, if there are any sheet metal parts here, those are automatically treated as shell elements. So let me try meshing it. Let me try it. Yes. Okay. Okay. So if you observe here, this part, which was actually a sheet metal part, software has the ability to automatically convert it into surface and mesh it with shell elements. Now, an exception, you may not find this in any other software wherein we are treating appropriate geometries appropriately in the simulation part of it. For example, solids remain solid or will come with solid elements. Sheet metal becomes surfaces and wet become beam. And this is an interesting thing. This happens when we create a new study, and I believe it's a big difference. People end up spending hours together to create surface elements and beam elements. And for software, it is seamless and it happens in a very easy way. Okay, looks like some question. When it comes to sheet metal, will the simulation automatically mesh it with shell elements with the center offset? Yes, you are right. So typically for sheet metal, by default, the surface is created at the center of the sheet metal part. If I to show you here, get a good view of this. Create plot, uniform settings, model. There is it not visible? Superimpose. Okay, that is shows me. Hide it and okay. I'm not, oh, it is visible, but a very light colored thing over here somewhere. So this you can see that it is sitting at the center of the sheet metal part. So they you think for our software, please use it appropriately in demo. Very good demo tool when you are saying we need not spend much time in the meshing part of the software. Example, we are actually doing some more things like we divide the part into a particular section, and we are concentrating on that section, etc. So yeah, interesting, or maybe something different that I need to highlight here is more of symmetry. Okay, so as we saw the way we treat symmetry in case of solid elements. When it comes to shell elements, it is a little bit different because okay, frankly, not much difference. Just that we are selecting the edges, and that's it. But if at all we are not selecting the edges, but you want to manually give it, then ultimately we need to give a bit more thought in case of shell elements. That's it. And if I put it simply, we need to just restrain the degree of freedom particular to this particular surface where it is being held. You can use the reference geometry option and hold it. That's it. not have this option. We had to imagine all the things and do it. Even did not have the option of visualizing the location of the shell element, and made a big difference. Comparison also of of the between solid and shell, and that helps. Just having a glass of water. Shell, yes. So as discussed in the last few sessions, do this comparison of solid versus shell, etc. But please remember, when we are moving from solid to shell, it is with a reason, and the reason is I cannot mesh the solid geometry with solid elements, and I want to use shell elements. Obviously, we are moving because we are not able to get accurate results using solid elements. So there is a point in comparison. But of course, if you have the time, if it is a small geometry, you can play with the number of elements. Nothing wrong in doing that. You can have a huge number of elements on the solid part, thin small part, and compare it with a shell part in different geometry. Element shell elements mid surface is fine. This I'm not sure if I need to cover. I think it should be okay. This is more towards modeling part of it. Guys, fine, thin versus thick. Okay, here it comes. If I put it simply, when we are saying thick elements, we actually, okay, first of all, there was a question which I already answered on that day, first day, the ratio. Okay, if you see this thin membrane like structures with the span thickness ratio larger than 10. Okay, span to thickness ratio. So like it is confusing over there on which length to be taken as span. I would suggest to take the smaller length because that may be looking more realistic. Divide by the thickness. If it is larger than 20, then obviously it is okay to use thin elements. And to put, if I put it simply, in one we are saying this are uniform across the thickness. Now this kind of assumption, try to understand, it is a kind of assumption. Whereas if it is a thick shell, then obviously even the theory used is a little bit different. I see at the top it is a kind of it looks like more of a Kirchhoff plane at the end of the deformation is using the Kirchhoff theory, and other one is using the Midlin theory. As other for thick elements, as yesterday, any shell element that you are creating, is fine to use thick elements because obviously you are considering all the things. And obviously, when you use thick elements, they are taking a little bit more time to solve than thin elements. Whereas, ensure you are selecting only the right geometries for thin elements. If you do a mistake in replacing geometries with thin, then obviously messing it up. Okay, so I think with images in terms of results, the explanation is over here. You observe it is more towards the displacement of the mid plane. Okay, basically in thick shells, the mid plane has relevance. It can change. Apparently, the outer planes can also change. Okay, in the case of thin, it does not happen so. And the bottom, it shows the linear distribution of plane stresses in both thin and thick shells. See the difference how it can happen. And if it is to be used in common words, I would say thick elements are far more realistic than thin shell elements. I personally tell my application engineers blindly use thick elements, no issues on that. If you have thin elements, give an extra thought on what has to be done and what not has to be done. This is what it is. Any questions? I would have some questions on thin and thick cell elements. It neglects deformation and stresses in through thick direction. Is considering it, but the shear deformation in the two direction, it is constant. Okay, and I think this is what I showed you in the software. Should be okay. Examine the mesh colors as I told you in the first class. From the simulation options, if you want, you can play with it. Quick, even after creation of the geometry, let me have a mesh here somewhere. Can I show you the mesh? Okay. If right mouse button click, option called as flip shell element. So it can help you. Okay, this happened. Okay, this is a surface thing. So didn't I select it? But basically, this is the option will help you in flipping the shell elements at appropriate location. So only this shell is flipped. Other than this, please, if you see such a thing, stresses will be incorrect. But stresses will be incorrect. Normal directions are very important for shell elements in huge geometries. By the way, by default now, the shell meshing solver has capabilities by which it can actually ensure connectivity or smooth create element. However, if the solver has failed, then you can do it manually. This is the way. Okay, let me go back to clear alignment. Okay. So this explains a little bit more on if the shell alignment is incorrect, how the results can go bad. But you also think it in a common sense way, wherein imagine shells aligned in the positive z direction, other one is in the negative z direction. The bottom surface is obviously different in both the surfaces cases, and the results will obviously be different. Let me to show you the results also at least of one case so that we can have a look at what the options that the was there already. Let me edit it. Okay, here in the options you also get these four different options for shells. You can see the results at the top, you see them at the bottom, you can see it at the membrane, that is the central part of it, and we can also see bending stresses. So these are different options that are available, and will definitely go higher if they are not aligned properly. Second, sometimes especially if it is a thick shell element, ensure check these things. It may be a case wherein the top stress are lesser, but the bottom are more. In some cases, membrane are far more important on the bending as well. So you might want to scroll through all these stresses to check which is more. You can also do an initial, how can I say, the initial judgment and think which could be more, and then directly jump onto that particular stress. No issues on that. This is how it is. What else? Shell. Yeah, use a bit of example on this. If you see this image over here, it is telling you if it does not align properly, you might end up seeing such kind of result. Of course, I told you the software by default at the global level, you'll see the option of automatic realignment of non-compatible shells. So try to section or a row of shells which are aligned in a certain direction and try to align them. If they are not, then it will. But of course, it's a huge geometry. There are enough chances of this being failed. Ensure you do it correctly. Okay, there's a new feature which we have introduced recently. Let me go both the places. First of all, in terms of results, we will see this option called render shell thickness. When we can actually see the results at the thickness, you are actually seeing the thickness of the geometry. These are more of rendered results. It may not be as simple and straightforward as that when we do it by a probe, but this is how it is. And also have option for, let me check if I can do that. Here it is. You can, so mesh can be seen in 3D. It's not possible before. So if it is, first of all, training part is different, but in demo conditions, if you do not want to confuse the who is not comfortable with solid shells, etc., you can use this render option and behave as if it is an entire solid geometry or a uniform mesh has been used everywhere. Let me go back to this. Thickness in 3D. Okay, this we saw. I had loads. I think I'll not concentrate too much on the loads and boundary conditions. That should be good. Okay, this is there, but as you saw, now the software is directly giving the option to select symmetry, and it will do it internally. But in the past, it was not there, and it was a big confusion on how to apply a symmetry boundary condition on shell edges. And this is how it looks. This is where this chart had to be remembered and done. But the easy way that I used to tell users was any direction perpendicular to the surface will be having a 0 restraint. That's it. But that which you might to use if you have the option in the software of symmetry. This is fine. Plot one message. I told you this. Should you error? It's fine. Probe it. Reaction forces. Deforms. This should be good. 7 close. The comparison being done. Computational efforts. Huge difference. Okay. The K is using the sheet metal part, and there you'll see how a sheet metal part is automatically treated as a how can I, that it is treated as a and that times a huge shiver. So if there are cases wherein you have solid geometry and it's easy to convert it into a sheet metal, you can convert it into a sheet metal part for analysis purpose, and it will be automatically treated in simulation. Summary. Gone now is the challenge, and Some things were discussed orally and unorally. Let's start off. Questions. Okay. Can I have a full view of this? Full. Okay. Yes. Can I do this? So, okay. Let's question. Hello. Chat window as well. Uh, check how is the participant list now. Okay. Looks good. Enough are there. Fine. So let's take the first question. Model contains sheet metal features. The corresponding shell mesh will be formed automatically on the very simple answer of the sheet metal. The thickness of the shell features must not be specified manually. What do you say? Quick one, where is the answer? Second one is may not, and we not. Okay, we'll go second question. Excellent, Ryan. Thank you. Second one, when creating shell mesh manually, it should be defined on the dash. So what dash should be defined on what? Mid outside face or inside face? The dash result in acceptable difference. Okay, this I would say an explanation as well as a argument. So please let me know your thoughts on this. First of all, what's the answer? Outside says outside face. When creating shell mesh manually, it should be defined on the outside face. Any other thoughts? Okay. This is frozen answer. That obviously what I say you can have a good argument against it. So take it. But say that if you think of an ideal situation, absolutely ideal situation, it would be on the mid plane. Firstly, if it is a solid geometry, we cannot locate the surface inside face in the mid plane because we don't have a mid plane, and might end up looking it on the inside face or the outside face. So placing them on the either the outside or the inside, the rate is acceptable if the difference is, now this is an interesting thing. If I place it on the mid surface, inside surface, outside surface, where I place it, the difference will be very, very, very low. That is as low as 0.0001%. This is the kind of reality of shells. Other down, of course, these options are present in the software. Visualization can be done, but from a theoretical perspective, it should not matter. I can place it anywhere. Other way, and the results variation should be minimal. That is as low as less than 1%. Okay, saying that if it is more, and if you are doing all the things, everything looks good, but yet if the difference is more, then it is a worrying thing, and that tells us that this geometry is not eligible to be handled by shell elements. We should go to solid geometry, right? At the point, it's a small question as well as a explanation. Hopefully you understood it. Any questions on the topic? If not, let's move on to the next question. shall be used to mesh thin like component. Characteristic span. So I think the span which we discussed, ratio indicating when to use solid, thin and thick shells are. This span T to be thickness. Okay, and we are discussing the ratio. So if this ratio is as if L by T is less than what, we can use for solid elements comfortably. First day I mentioned this thing, 5 looks good, and thick is between 5 to 20 and thins are about 20. Okay, just often remember it. It is more of a rule of thumb. Remember the answer to this second question. This is equally important. We see a thing between 5 to 20, but enough thick that we might need a solid element. So take appropriate decisions when you're doing practical examples. As per theory or as per rule of thumb, this is the logic. 5, 20 and more than 20. This is a simple straightforward question. So we have 200, we have 75. Simplest edges, free edges. 200. Thickness is 5. Dotted and dashed lines indicate simply supported hinge and free edges. The best element type fit for, so by loads and boundary conditions may not matter much for elements because they can consider bending as well because rotational degree of freedom imbibed in it. So do not worry too much about it, but huge amount of deformations are happening by which we expect the stresses vary within the thickness, and I want to see it accurately. Then obviously I need solid elements. Right? It should be okay. So use for this thin, thick, or solid. Other one, just tell me the ratio. That's more than enough. So the ratio that we get is 15, and it is correct, right? Let's move on to accurately model. Oops, what happened? Okay, to accurately model the stresses and strain gradients, a minimum of dash draft quality or dash high quality should be required in the through thickness of the. I think this is what we discussed in few classes. I would prefer answering myself because we are adding a draft quality here. Typically, what we speak is 2 nodes across the thickness. Understand nodes. So it's a high quality thing in itself. It has 3 nodes. Assume there is one more element. What we are getting is 1, 3, 4, 5 nodes, and that looks good. So at least 2 elements for high quality and at least 3 elements for draft quality. So this again a rule of thumb. For more accuracy, we might need more, etc. But as per theory or as per common guidelines, this is what it should be. If a sufficient number of elements generated, solid, thick, shell, thin elements will always provide the most accurate solution. We sacrifice a little accuracy by using shell elements to mesh thin features because yes, C equal to draft. It's ran, you are right. 2 elements for high is perfect. Okay. The last question, I think it is easy. If a sufficient number of elements is generated, okay, number of solid elements is generated, whatever you might see, it will always provide the most accurate solution. Excellent. We sacrifice a little accuracy by using shell elements to mesh features because. So where accuracy in case of elements. I think for this, the best thing is the expression that we had or the discussion that we had in case of difference of results between thick, etc. Put it simply, if you are thinking of having accurate results across the thickness, then it may not make much sense. We need solid elements only, if of any kind of geometry. And from a software perspective, if I remember rightly, there are some limitations. I should say from theory, but something like that, that we may not be able to simulate thermal thermal results or thermal simulation using shell elements accurately, and we don't have it. So there are few limitations that come in that direction. Okay. Fantastic. Any questions on this lesson, lesson 7 and lesson 6 with on compatible and incompatible mesh? So not sure who was it, but if I remember rightly, you were asking about do we have example on creation of edge weld? I think this is the one. This example can be used for understanding and using edge weld connector. Uh, this was creation here. As remember, edge weld connector is available in simulation professional only. I think uh, before lesson 8, we take a quick break of minutes, and we'll start after that. In the meanwhile, any questions from lesson 6 and 7, please ask. I will be around. So now it is almost 10 to, we start by 10:07. Hmm? Let's meet. Guys, any questions as of now? Okay, now most of us are comfortable and know this concept that in case of solid elements at a certain node, we will have only 3 degrees of freedom. Oops. Yeah, here it is. So you see here, it has only 3 degrees of freedom at a given node, whereas when it comes to beam or shell element, it actually has 6 degrees of freedom. Okay, so we actually combine these two elements. This only problem that we face, that is how I'm going to transfer the freedoms to those transfer of freedom of a solid element. And the biggest challenge of meshing for software. Of course, we need to be aware of this problem is there and it is handled in a certain way, right? That's the only difference. So this is how it is. This chapter is on mixed meshing. We are mixing shell and solid elements, and we'll have a look at what are the important things that we need to take care of. So by default, when you fix a shell to a solid, high chances, the way it is connected, some things which happen internally, it is not exactly ending up into a hinge kind of condition. Now we have moved to a condition wherein it will actually try to imprint the cross section of the shell on the solid, and it will try to have it connected across the surface in not an edge. So that is a bit different perspective. By saying that the way it works or the way it happens, it will not transfer the rotational degrees of freedom, the displacements coming or the movements in the rotational direction, the solid mesh. So we need to handle it appropriately for that. Saying that, okay, this is an example of a pressure vessel and joints, especially what you are seeing here. These are the brown part over here. Unfortunately, because of the overall dimensions, the current, and we want to simulate the bolts as well accurately, we may not be able to simulate it as shell elements. In such cases, we end up mixing solids and shells, and in these cases, we need to be aware of what happens, how it goes, etc. So, frankly, from a perspective or a process perspective or a theory perspective, the only difference or the important thing that we need to understand is this one. That's it. That is, when we are mixing solids and shells, we are transferring rotational degree of freedom. Whereas mixing shell and beam, it's fine. Both have 6 degrees of freedom. Whereas mixing beam and solid can again create a complication. Now, it's not a huge complication. It has its own means of handling it. It is enough if we know and manipulate the things appropriately. Perspective, I believe there is nothing nothing different in this chapter. Let me check. If it is, then I'll cover it. Okay, we the shell manager. Let me just show you that. This was a new feature which we introduced in the last version. Those all these old files. Let me go open here. Lesson 7 and lesson 8. It's a big geometry with multiple parts which are different differences or conditions. Then we might be required to use their option. So one option would be directly right mouse button click on each of the entities and going for editing them using the define selected faces, etc. The other option could be this shell manager. So this one is a nice exhaustive way. At this is a uniqueness for software. You may not find this in any other software. Uh, I can say it is a market differentiator. So in one single front end, you are able to manipulate all the shells in this entire setup. So different things that you can do. First of all, you can create groups of these shells, which can further used for application of loads, boundary, not loads, maybe probably material properties, thicknesses, etc. or location. You can decide whether it's a thin shell or thick shell in a single thing. Thicknesses can be defined in the single front end. In the past, you had to go to each and every shell and do it. It is like you are reducing the work of almost 2 to into less than half an hour. That is the best part of this front end. Materials, or there we have the option to flip them. This is interesting. Flipping was a huge task in the past. Now it is just a button click. You just know which shell it is and flip it as per your requirement. You can add whether it should be bottom, middle, etc. And finally, whatever name it comes by default. All this can be visualized. The thick variations can be visualized in the form of colors. Color is given here. You can see that. You get if different materials are given, even those can be seen in the form of colors and offsets. Typically, all these things can be visualized on the front end using the options over here. So this is an excellent utility for manipulation of shells, especially shells, and it is a new feature which was introduced in 2015. So and that been included in this training manual. Set we already discussed it. Bottom is fine. Note this should be okay. Other indices. Okay. This has been shown here, but in case you guys are not aware, we also have this material properties which come from the global service provider. So customers who are with simulation professional and under subscription, they can actually click here. Yeah. You quickly going to a website. This site is basically from this company Materiality. It automatically checks your serial number. If it is okay, then it goes here. We have few more variants, and these have been segregated as per the requirements of an analysis. You can which kind of analysis you are doing, the material model that you need. You can just select from one of these available, and you can click locate material. Huge and exhaustive, but it is nice. It is more than what we had before in this one. Plus, they also provide an option to request for different materials, and they can. By the way, after doing that, actually you can download the necessary material from there and use it for your purpose. To this. Fine. I need to discuss much on this. Bulk and Chevrolet. Okay. The mesh failures, I don't think I should be going deep into it. I think it should be okay. It's a front end option, and you should be able to do it. Incrementing, okay. Is again a option which is present or was introduced in one of the recent versions, which is as incremental meshing or meshing that happens on set geometries. So you can see here, even when you right mouse button click on any of these parts, you'll see this create mesh option. There could be a case wherein this part is only failing for mesh, and you want to remesh it with a different boundary condition. So sure, first of all, to get this part going or meshing, it is as you are meshing this part, you can only select right mouse button click on that part and start meshing it. Second, play with the size of the mesh, etc., and you can manipulate all the finer details. On doing that, it will try to remesh only that part with the dimensions that you are given or features that you are given. And yeah, just to show you failure diagnostics, it comes somewhere here. So I'm not showing any failed meshes, but if I talk about different options, you can see here incompatible mesh. I believe after lesson 6 you have understood the difference. So one of the methods of getting a failed mesh going is to use a incompatible mesh. Show solid bodies which failed to mesh. Yes, we can see them. Visualize, yes, which is the particular part which is not meshing properly. Mesh for all bodies, mesh control. So mesh control tool will come. We can select the appropriate geometries and refine the mesh for them. And check geometry. It is just a tool which will help you find out small entities, etc. And we can. So or we have thickness analysis, simplify model for meshing. We get rid of certain geometries, geometry for failed, etc. So one way these are coming through a wizard and they can explain. They also be seen as a knowledge resource for you to understand if a mesh fails, what next, what I need to do. Okay. And finally, if you want to improve upon certain things like say you want to concentrate on imaging the geometry. Now you know that is one of the options what it does. Even without this advisor, you can directly jump onto the geometry. These are SolidWorks option, not simulation options. They have been just given over here. You can directly go to the appropriate location, do the necessary changes. Okay, I close this. Let me go here. Excellent. Go to the question. So, after all bonded contacts, successfully meshing a complex assembly, you attempt to solve the analysis. The solver displays the following error message. The iteration solver, the solver has numerical difference. Model may not have adequate fixtures. No results saved. Some of the bonded contacts are defined incorrectly or not all as it is easy to unintentionally forget to define some of the contacts. Proper fixtures or bonded contacts makes models unstable, resulting in the solver displaying the above message. This question, how to locate missing incorrect restraints or bonded contacts. Yesterday we had a session, we discussed on visualization of the basically contacts all over the geometry. That is one of the options which should help you doing that. Apart from that, the set of different things, if at all you have the flexibility, you can use a frequency analysis. Typically, you can use a frequency analysis, the analysis, and get to know which of the geometries, which of the parts are flying off, and you can improve upon it. Finally, you can also use soft springs and solve. Obviously, when you are using soft springs and solving, you are not solving for accuracy, but you're solving only to find out the problem is. So that is just using that to understand which part is not completely constrained. Okay, so these three, and one option which I personally use sometimes is get off all the loads have stands no problem appropriately, and then apply gravity, and that should help you find out which part is falling down or which is typical solver might fail. If it is iterative, you can stop it and see it, or you can use soft springs, and that can help you visualize it. So few different options. A few are commonly used, few from my experience, few here he'll be highlighting more on the visualization of context. These are the few different things. And I'm sure if it is assembly, especially if it is a big assembly, you all should have faced this error as of now. Those already working on simulation, and frankly, it is clueless. And obviously, you may not find, or you'll find too content all over to understand what could be the how to go about it. But any questions? I have a question and I gave the answer because it's a bit lengthy thing. Anything that you want to ask me on question number 1, please ask. If not, the second one, a bonded contact between shell and solid components does not require a local bonded contact condition. Yes, good. Some or the other, it was present in the discussions inside the software, and I would say I'm discussing it, but I think let's see what is your opinion on this. Say if a bonded contact between shell and solid, if any, then does it require to be bonded contact, or can a global bonded contact condition detect or a shell to a solid? Interesting. What do you the silent? I can see the attention growing. Wow. The right simple answer. So even though we have the global bonded condition, thank you, Tony. We need to, or we should create bonded contact for connecting shells to solids. Okay, remember this. The next chapter, wherein it is on beam elements. I ask to you guys to think this a chapter of mixing of shells and solids. If any questions, please ask. Give a few seconds. Window. Is asking if this training will be recorded? Answer is yes. Or that is one of the intentions of having this. I will record it. Of the recorded sessions will not have any feedback from me, or you cannot ask questions, but of course you can in the future. So please, I'm not sure I will share it by default, but please work with me and I should be able to give it to you. Okay, let me check the other questions. When doing, okay, let me make it bigger. Would it be advisable that the final iteration for results to be all solids? No, there is no such thing. As I told you, we are moving from solid to shell because we cannot mesh that geometry with shell elements. Point, that's it. If I could do it with solids, why not do it with solids? Why do I want to move it to mesh shell elements? That's it. There is a reason for doing that. For example, the first few rounds be mixed meshing. The final round where we choose the final results be all. No, there is no such rationale. If a geometry you don't want to play with quick things, it's fine. But think about accuracy. Shell elements can give equally high accurate results. Rather, they are less and far more accurate than solids in many cases. But the wherein we are moving from solid to shell, because we cannot mesh the geometry with solid elements. That's it. Come to beams. As I mentioned you, by default all elements will be treated as beam elements. So no huge amount of time a user ends up spending in creation of these elements is saved. Okay, you might find me going a bit more faster now because I wish to cover the simulation manual, at least the first training manual, and then in the frankly I preferred to finish the motion as well in these 3 days, but I don't think I can do it. I have decided to extend this training in the next week. Probably it will be on Tuesday, Wednesday and Thursday time. The same links will hold good. I'll cover simulation professional and motion in those 3 days. So try time. I know it is a bit of last minute thing and may be difficult, but of course I'll be recording if I try to attend it live and use this opportunity. I could have gone faster, but it does not make sense. It is good that you understand all the topics. I want to take all your questions, and this is a good opportunity for you to learn and get the answers from me directly. So I already extended the online WebEx settings up next weekend. Just a setting. But other way around, I intend to do the motion and simulation training, simulation professional part of it on 17th, 18th and 19th mornings, 9 a.m. to 12 in the noon. Okay. Single time. Let me go back. So if you see this entire setup, it is made up of weldments. At least over here, that should clarify. So this is made up of weldments. So typically when I create a new study of this, automatically these weldments will be treated as beam elements. We don't worry about it. It could be small entities. Sorry, not an exception, but they are treated as beam elements. But beam theory says that this is not as per the software, but as per beam theory, the beams needs to be of at least a certain amount of length. They can't be smaller than that. For them. So if that is the case, then the option like by default beam is correct. Now let me try to mesh this. Let me check. Okay. as it all looks good, it has created it properly. But if this is not the case, and I want to tell the software or the software which is the neutral axis, that can use this option, right button click over there, define neutral axis, and I can select one of the lines over here. The option is lines. That can be used to define the neutral axis of that particular small part. So for small part, the software may not be able to understand which is the neutral axis, and using this option we can actually tell the software which is that. Okay. Second, if here there is a pink colored joint, okay, this means that over there more than one beams are getting connected. Okay, more than one beams are getting connected. There is also a gray colored thing which is more of a end joint. Those who are not aware, you can directly right mouse button click somewhere near the joint. Okay, no, I should be in the edit joint. Okay, right click, edit, and somewhere in this option, I can actually right mouse and click on that joint, and it show us which are the different members that it is. Why can't I make this big? Okay, anyways, it can show us which are the different members that are getting connected using that particular okay. If you want, or if you want to add, subtract, change, etc., you can actually do that by just, you can select in that particular set. I'm sure if it will work for this case, but I'll try. No, it worked. It worked. So it has basically, it has done a funny thing wherein there is a joint over here. The connection for the beam has gone down. Some of the other, and this is an incorrect thing which I'm doing, but you can use method to change the members that are present in the joint. Now I'll revert it back. I'm just unselecting it and calculating it. So now it has gone back to a state wherein, yeah, now it should be interesting to do. Let me check. Okay, let me try to select the point over there. That's beam end, which is here, is actually angle coming to end, but I want to connect this beam to this actually other beam or the point as well. Let me see if it does that. Yes, it did it. There are two joints here, both are connected by these two beams. Okay. But actually this may not the location where I should be showing you this example, but the joints can happen in this way. If you display the neutral axis, this center, that's fine. One more option which okay, quick one. I need two weldments which are within 0 touching distance. If you see this thing, if you can also specify the value of this particular gap you want to permit between two weldments. So I can do that and give the value in terms of units, whichever you want, and that should be able to help you. So there are two edges, two nodes, etc., which are within a gap of 5 millimeters to be merged using this option of gap. Okay, so this is one thing, and I want to ensure I have one more thing. Let me this option of the definition. Okay, restriction properties. Okay, by default, based on the material properties, the software will take the shear or the torsional properties of a beam. Past, we did not have this option. Beams would neglect torsional shear stresses or properties. Now we do have this option, and we can actually those values manually, as well as software has some options by which it calculates those values. as of now? The strengthening option is present for beams as well. You can mouse click, it is over here, and same happens for results. You can right mouse click and directly go to uh, the edit definition dialog box. Okay, do it. Do a quick one. The joints. Okay, the joints can be manipulated or treated with these three different kind of conditions, or rather. So I told you, okay, if I go to manual, I think that should clarify. You can see few conditions. Difficult to imagine all these conditions and use it. Most of the times we will obviously leave it at the rigid condition. That is that all 6 degrees of freedom from each joint are transferred to the other joint. Okay, other way around. Um, if you remember, we have already discussed that beam node has 6 degrees of freedom. Use this option, or we are telling that all these 6 are getting transferred. If you don't want, there could be cases like huge bridge structures, etc., which are connected with pins. Those would be cases wherein it is a kind of hinged condition. Okay, it is a hinge wherein only the translational degrees of freedom are transferred, or it will be a slide condition only, wherein rotational degrees of freedom are transferred but can actually slide. So those manipulations can be done. I have rarely seen users comfortable and using it, but the option is present in the software. And around, you can also treat all these beams as elements. These are more kind of elements, and more of stiff elements, not have bending into them. They just transfer linear forces. One of the things which is useful when we see the results is the direction of the beams, and the option is unfortunately somewhere inside over here in the beam element. If you I either use this show beams, and we can visualize the X, Y, and Z, or 1, 2, it is showing in the form of 1, 2, and 3 direction. So here the red one is obviously axial, we know it, and the other two are the planar direction. Let's try if is this with all some boundary conditions. No, let me go to the study. I'll solve it. Okay, so for let me see, show you all are the different results that we have. Edit definition. You are getting these few different kind of things. So upper bound of bending in direction 1. Now important would be what is direction 1 and what is direction 2. Okay, for beams. It's, and I think this image on page 34 should help you understand. Components, extreme fiber location in direction 1. Longest side is direction 1. So you can see completely the side which has longer length is in the cross section is direction 1. And one is direction 2, which is completely smaller section. So it is easy to say here, but difficult to understand when it comes in the model. It could be cases of the cross section, that is direction, the length of direction 1 and direction 2 is same, and it's a bit of confusion there. At least giving this content, but in the past there was definition or no idea from the developers on what to see, and we ended up seeing directly the results and then deciding which is relevant for us. It happens that in the bending direction, in direction 1 you might see higher loads, and that is what is important for us. The or other way around, typically one of the directions will show almost zero behavior, and that helps us other direction. Even though this explanation is there, we can understand it, but ground reality, or most of the times, we end up actually seeing the results and concluding what is what. So we can also see the torsional thing. So these are the there. I told you the rendering option is present for beam. Okay, and secondly, for beams we also get something called as least beam forces. Okay, you can actually list the forces in different beams, or the stresses. So at different joints, that is, there will be one and N2. You can see axial, shear, moment, etc. Those can be seen. These can also be visualized using a beam diagram. Where did it go? Different beam diagram. So in here, obviously the direction makes a difference. This should be okay. I think rendering does not make much sense here. Let me name it so that we can play with a few things. Okay, yeah, it's difficult to understand on the geometry, especially if you are comparing with some theoretical thing, then it makes a bit of sense. This particular beam, if you are in the shear force variation, then it looks like this. Most of you might be remembering from your college days the force diagrams and the bend moment diagrams. There are a few good images which should those few good results which you can do manually and compare with the software. This one is around 3000 Newton, the red one. So if I go direction 2, also, and kind of haywire because of the other thing, but this is more completely higher. So obviously my concentration would be more on direction 2 than direction 1. And bending. So, and by the way, I'm saying it only for one beam. I selected a single beam here, so the visualization is understandable. There's some question here. What are these values for torsional constants obtained? These are physical properties. The torsional constants are physical properties. So it's more of there. You will find many theoretical formulas. Either not if our knowledge base has it. I think it should be having it because in the past we didn't have it and we had to do it manually. So and if not, some values by default software will populate as per the cross-sectional details. It has its own logic. It will do it. But formulas are easily available for that. Can we plot the diagram in Excel? Palins, I didn't understand this. You want to plot the diagram or do you want to export the results? I guess you are talking about export. So this, let me go here. I guess forces export. Yeah. So if it is export, then I think you should be able to do it. Let me check. Yes, you can do it. Say you can export to Excel. You can do it. Okay. While able to export, you can select units, all this, but problem imagining which beam is which, and it becomes a bit difficult. After you are doing some comparison studies with a small model, it's okay. A beam, a big model, it's a bit difficult thing. Let me check something more. Let me check this edit definition. To do the calculation, here it is for the constants, etc. And this should help you. The calculates the torsional constants for most of the beam profiles. Formulas, oh, here it is, he has given it. For formulas of torsional constants for various cross sections, see reference formula for part. Wow, to go to that book and check it. So, really, those are available for different cross sections, and you should be able to get it. Let me check if our knowledge base has it already met in it. Constant. Yes, it is. It has something. Torsional load, directions. Yeah, better explanation on the directions of a beam. This particular knowledge base article, or you can just try searching by these words, torsional constant. Okay. And bending in low direction one, bending in yes, yes. So David, I think this should help you in understanding in a bit more detail on the torsional constants. Note down this number, or you can search by the name. Can we do unity check on each beam based on AISC code? Yes, good question. I don't think so. There is any ready-made thing as per that standard. So, I'm afraid I don't think we have that one ready-made in the software. Can you just drop an email on what exactly you want, or who wants, or what help in understanding this? Okay, need to check. I shall not be speaking on that. No. Yeah. Okay. Any action, guys? Is a topic of actually more of elements? Anything specific? Please ask. If I missed out on anything. And the next chapter is more of mixing of solids and shells. From there, nothing much on the theory perspective or there, but we'll quickly scroll through that. But yes, the mean any questions on this topic? Let's see the questions that the training manual is offering. How many degrees of freedom does each node of a beam element have? We have spoken about this quite enough times now. You should be okay with it. freedom, right? Okay. What is the difference between beam elements and truss elements? Yeah, good question. Any points? There a beam and a truss. Difference between a beam element and a truss element. One is okay, good point. True make the difference. True. Certainly, beam has 6 degrees of freedom, truss has 3. Second one is uniaxial, more of the load transferred in the axial direction only. Or I put it simply, as Alex Hong has written, can support bending. So beams support bending, whereas are not supporting bending. Let's move. Oh, should I kept the chat window open? For beam element to produce acceptable results, the length of the beam should be dash larger than the largest dimension of the cross section. Or what is it? For a beam element to produce acceptable results, the length of the beam should be dash times larger than the largest section. Yes, frankly, I did not discuss it during the training, but any thoughts on that? This is what we are using to define length of the beam, whether it's short or not. This is what we are defining to define where we need to find the axial direction of the beam. theoretical thing. It is a guideline, kind of guideline that the length of the beam should be at least 3 to 5 times for it to behave as a beam. Okay, to understand, to behave as a beam. The same rationale is that we were speaking in terms of shell elements, that is in terms of thicknesses. Does not make any sense to represent a geometry which is not 3 times of its cross-sectional length, cross-sectional dimension, to represent as a beam. But it could be a case wherein it's a huge number of beams and there is one small part here and there that do not worry about. It's okay, we are using it only for connections. Then you can use the option available in this software. Frankly, in the past, we did not have this option. We did not treat small beams as beams. There were requests from the customers who wanted it. They were happy to neglect, and we introduced this option of bending it. Yeah. Really, it should be 10. Nothing wrong. At the software, like as I told you, it works now even for even in a square box. Even a square box can be treated as a beam element. When it comes to manual calculation, we're talking about 3 to 5, and of course, as the training manual says, 10 times is equally good, no issues. This holds good for aspect ratios also. They speak about 1000, which is kind of meaningless, so huge. We speak about 10 to 20. So there are 2 to 3 different aspects. One is what is as per trainer. Second, what the software can handle. Third, ultimately what we do in the software, or when we apply it to the software. So if it's an exam question, better to say 10 times. No problem. Beam element. Okay, the bending stress plotted on the 3D profile of a beam element cannot show the variation through the thickness. Yeah, what do you say? Can we see it or cannot see it? Bending results. You can see them. Better to say it. Let me go down. Bending. Is there anyone which already created? A verb of bending next year. So we take if it is equally high. Whatever. Bending stress. Okay. Now augment across the cross section, no difference. Let's try to pull out a profile so that I can do some changes. Let repetition much variation. Okay. I cannot explore this option before, so I'm checking it now itself. So with a let me change the direction 2 also. Let me check it. Definitely, it is showing some variation at the thickness, unlike what we see in the case of a not profile. So non-rendered, these are the actual results which are calculated at the beam. Thereon we'll use the profile to extrapolate the results across the cross section, and it is taking all the appropriate considerations for calculating it. So sir is definitely yes, it can show the variation through the thickness. Okay, any other question on beams, guys? Before lesson 10. So much questions. I am okay to proceed because even I have to cover a huge amount of content in the last 1 hour that I have now. Okay. Of course, this lesson I told you nothing much in terms of theory. It is more of like when we do the training personally, we tell users so do this because it will take you at least an hour or 2 to get going in the proper way, because it's a huge setup with loads and boundary conditions. But this can help you learn and understand and apply whatever knowledge you had as of now on a comparatively big model, you come across very different kind of conditions in which it is created. I'll stick to the same logic wherein I'll not go much. As you saw, it is more of a software thing wherein you are following a certain process to do the setup, create it, and solve it. Those manual, please go through it. Even phone should be fine, nothing wrong. But any questions, ask. This is a good example, not only over here to learn, but if you are doing any demos for the automotive industry, use this example. Even nice image, the exercise on frame rigidity, and if it is a demo in the automotive industry, then this can be of use. Design study. Okay. Design. Now there are that. Okay. First of all, let me open the model. Okay. Option, first of all, where it comes, when you right mouse button click, you'll see these things. Create a new design study. Okay, this option is present here. Of course, the module that you all may be having a simulation professional and premium, and you should be seeing similar to front end as me. Particularly optimization is not present in design study. It is more of what we do is we change certain variables in setup, and thereon we see the results as a variation of those how can I say variables. Okay, go to one of the designs that has been created. Let me go to variable tab. So if you observe here, option that this front end is giving is we can actually change. Now in this case, we are changing the thickness in the option range with step. Okay. Typically when you click here, add parameter, you have different options. One of them, you can create a new variable. It could be a model dimension, and we can specify an initial value for that. That has been done here. Thickness, this and thickness, we are saying it is varying from 1.5 millimeter to 8 millimeter with a depth of 0.5 millimeters. That is, it will be 1.5 to 2. Then in terms of constraints, here we are not optimizing, we are just visualizing or knowing what will happen when this moves. We are just monitoring stresses and displacement. That's it, nothing much. Okay. When the results are done, we get, is this solved? I thought this was solved. Okay, I can save it and check it also, but you can see here we have iterations at 1.5, 2, 2.5, etc. All these iterations are there, and at each of these iterations, we will be able to see the stresses, displacement, and whichever locations we have opted for. Okay, so try small difference here. Oops, I think it was there in the results here, which I missed out. Okay, that's fine, no issues. Okay, so the only advantage of design study is we are able to understand, or in a single front end we can do iterations for inputs. Now these inputs can forces done certain dimensions of the body, or even I think material properties as well. Okay, so typically we create a variable, attach it, and that shows us it. Okay, still a big model, and I should not have done trigger solution, but let it do what it wants to do. Let me go back to this PDF. Okay, so in this again, this is another automotive example. So demos, etc. Also, I suggest you take this thing. It is a small shock absorber and should be handy in explaining this topic. Okay, it is also useful in talking about world is different. They don't use design study. They might be using words like experiments, or they might be having some other Excel sheet or software by which they can come up with that they want to do, and those iterations can be further realized here. Mhm. Guys, I'm through this design study to check if any other topic that I need to highlight. If there are any questions, please ask. Properties of the design study. You should be able to see this thing called as fast results and high quality results. Okay. Typically, in a fast result, it is not actually solving for all the iterations. It's all for appropriate iterations, and thereon interpolate the results for the rest of the studies. Um, Obviously, if it is a linear study, a linear analysis, then no big deal. It should be okay. But if it is a non-linear, you should be able to see differences, and you might want to have high quality. But try to understand, design study is not design optimization. The optimization feature is present in simulation professional only. Over the software decides the variables to be used for results. So we don't have the control. Software has an algorithm which decides those variables, manipulates it, and then gives the results. Whereas in this case, it is only um, variables that are given by the user. So in Solidus Premium, we are getting and simulation standard, we are getting this option only. That is they're asking. Okay, I think I missed on. What is solution when the slender ratio is 2? Alex, this is about beam. What was the solution? Okay, in the past, the solution was only to create solid elements. We had no other solution, and beams would fail directly. But we can create beam elements and just give the axis. That is what the software is permitting. So rather, the software takes an axis automatically, but obviously because of if the slenderness is very close, then we might get a wire, and need to specify the what is I missed out the axis. And I guess you're also asking in terms of the question. So as David mentioned, oh, I think it is a private message he mentioned. In page number 368, they are giving the value, which is 10 times. So this slenderness ratio should be almost 10 times. The length of the beam should be 10 times of the section. Fast results decide which iteration to run. Any literature. There is no literature. We claim it is, or it is a reality that it is a company confidential. There is algorithm which does it on its own, and we are not. This algorithm is not revealed anywhere. And the messages to everyone. So the question is visible to all the attendees. I don't mind, and you want to send something privately to me. And frankly, I'm not sure whether you can see the chat window on your screen or not. Can I get a quick answer? At the moment, the chat window is on my monitor. Can you see it or you cannot see it? Okay, understood. So it looks like the chat window is kind of hidden. That's what WebEx does. So good, not a problem. I can safely see. Okay, fine. No, let's continue. Guys, any other question on design studies? Thermal analysis, interesting concept, and I have to convey a bit of segregation here. Please try to understand. Yesterday morning or on the first day morning, we discussed this topic called as more of a body load and not a stress load or a joint load. Okay, so please remember that. Now, saying that, also remember in or simulation standard, we can only analyze the stresses that are coming because of thermal load. So there is any temperature changes happening, we are giving an initial temperature in the properties of the study. There we are giving the temperature that the part is subjected to, and this variation or the difference is multiplied by the coefficient of thermal expansion given in the material properties, and we get the overall expansion in the geometry as well as stresses. That is it. We cannot simulate temperature changes. We cannot simulate thermal distribution in simulation standard. So this chapter there might confuse a few of the attendees, but remember this is thermal stress only. It does not include thermal distribution. We cannot see temperatures or temperature distribution. I guess there is a exam question as well related on this topic. Typically, different metals or different kind of components have a different coefficient of thermal expansion. I think I open this particular study. Case study, lesson 11. Let me go down. Case studies, bimetallic strip. So this is a bimetallic strip. That it is used for actually measuring the temperature changes also in thermometers or certain kind of measuring devices. So one is having the metal nickel. Okay, it is a nickel metal. And important thing which I want to highlight is the coefficient of thermal expansion. You can see it is 1.7 E here. The second is aluminium. Am I right? Is okay, 146. Okay, and the coefficient of expansion is 2.3 E5. Typically, it will be very small. It is less quantity. We are talking about per Kelvin, but it is kind of unitless quantity. By the way, this is an exploded view. Nothing to that, but it is actually like this. Okay, and okay, if I to highlight on the important things of this study, we are defining inner of this entire setup. Okay, this is very important. Reference temperature at 0 strain. That is, there is no strain in this body, and the temperature at the moment is 20 degrees Celsius. Or if it is in Kelvin, you can change. Second, we are specifying the temperature to which this body is going to reach. That is final temperature. Remember, a big mistake we all do. Our software should stop users from selecting nodes and edges over here, but they have kept it generic for all the front ends. We can select the appropriate how can I say, the bodies over here to nature. So you can see here the bodies. Now it is sometimes people know how to select the bodies, so you can either select the part directly from the front, not from the feature tree and not the front end. Okay, sometimes it gets confused, or you can use the filter and select it, or you can activate bodies inside the part and select the bodies directly. That is the only way to do it, a better way to do it. What is that? Second, ensure you are selecting the bodies, not surfaces. That's what I want to highlight. Second, the temperature, you can apply the appropriate temperature. So this entire set is increased from 25 degrees Celsius to 280 degrees Celsius. That is the only thing happening. So three different things. Number one, material properties, varying coefficient of thermal expansion. Second, initial temperature is given. Third, we are applying temperatures on the body. Now these temperatures can also come from a thermal analysis done. Okay, thermal effects. Okay, it is. Actually, so you can also get the temperature variation from a thermal study. Unfortunately, nothing in this one, but you can of course get from that study as well, or apply the temperatures manually as shown here. So see, let me take a start view, and if I take it here, so this is the way it looks. And it should be actually trying to open. That's what is happening here. You can see. One part is trying to expand more. The part is also expanding, but it is a bit less, and it leads to this kind of opening up of the part. And other one, if you see the stresses, each part is expanding in a different amount of value. So there can be stresses at this particular surface or the place where it is connected. Okay, what else is important here? Shear stresses would be higher here comparatively because the expansion is happening in the shear direction. Okay. And let me go back to the PDF. Any questions on thermal stresses or what we can do here, what we cannot? Can calculate strain due to shrinkage when it is cooled? Yes, can calculate. Yeah, not a problem. Okay, good point. And other way around, those who are aware of plastics and those who are aware of warpage, this is warpage. For plastics, we call it as warpage, wherein the part is changing in dimensions when it is changed from a certain temperature to the temperature. In this study, we are also, by the way, yeah, remember, typically for any material or any given material, the properties with temperature. Okay, the properties change with temperature. Let me check if they have already given it. Which one is expansion not given? I thought this is given. Not yes. The yield strength changes with temperature. At 25 degrees Celsius, the yield strength is so much. 2,4 this much. 316 this much. So if you have these values, those can be given to the software, and software will appropriately take the right values. And actually see these things. Most of the properties, we option give the variation with temperature. If it is not given, it will take a single constant value. And if it is the other way around, we are actually giving those values. Let me go back and enter a spreadsheet here. You can do that. Properties dependent assign model to okay. Yes, it was global bonded contact. I did not discuss or never came as of now, but remember a kind of option which is quite handy sometimes is something called as this sensor source here. You add a sensor by just right mouse button clicking. There are different sensors. There are specific sensors for simulation. You can monitor these different quantities. It could be a quantity of stress. See, at the moment it is directly populating over here. Stress value, obviously this is the maximum stress. And you do have these different options like model minimum, model age, max stress, etc. So this is what it was. Other way around, you can see there are one global mass. You can see here, this is the mass of the body. So for a period of time when I'm doing changes to the design, I want to keep a tab on the mass. I can keep on saying this. There is a sensor of aluminum here, which is not updated. You can actually click up. I'm not sure what this is created for, but sensitive sensor. which can actually be used to create a graph. So if I take a particular result here and try to plot it, let me do the option. Okay, these sensors are available here. I can directly create sensor. Typically, in practical conditions, when they do it, they have a sensor located at a certain location, and we want to compare. We want to compare the results that we are getting from practical conditions to that from the software. This is the best option. We can create a sensor, use sensor for plotting the results at the appropriate location. This does not make much sense. Yeah, that's okay. But these are three sensors which are available here and for as well. Okay. So this is the way the sensor option works. A handy tool while designing or monitoring the results or keep a tab on certain results at a certain location. Anything else? Stabilize the model. This is what discussed yesterday. By this particular model, if you observe, there are no restraints. They're not holding the model anywhere, and only soft springs are being used to stabilize it. You are right. We can actually, like, if we hold this model or restrain this model, the stresses would definitely shoot up. Just show you. Let's just play with this. I'll create a duplicate. I hold it at certain locations. 1 and 2. Let me hold it on the other. Obviously, doing that, I am restricting it from expanding, and the stress should shoot up. Okay, so it was last. You can see, okay, it has increased more at the end. 3.5, so 350 megapascals, somewhere around that. This lesser, yeah, it is around 260, 26 rather. Definitely, Tony, it should go up. Can it calculate strain due to shrinking when it is good? Yeah, this I answered. Can you reason the ends resulting in additional stresses? Yes, this is done. Questions, guys, while I scroll through this chapter. Okay, this thing option I never understood. Let me go to the option exactly. If you see here, there is something called as average results across boundary of parts. Now, typically, when we have multiple parts and these parts having different materials, we need to be cautious in the sense, obviously, the stresses would be different in these two parts based on their own material. So, this option intrinsically is giving us the capacity to either average it. So, you can see here a kind of difference between nodal and elemental results, but across two different parts of two different materials. So I'm selecting the nodal values. I'm selecting this average option. So it is averaging the stresses at that junction between two different parts. On the other hand, if I unselect it and again, you can see it is so very. Obviously, I believe it is common sense that we do not select this option, but typical for smooth visualization, etc., we might want to also select it. Okay. This should be okay. It should be fine. Nice image showing you how the results might be happening in over here. So see, especially the bottom thing, you can see nickel and aluminium. So in case of nickel, comparatively or neutral axis over here for all three, and based on the material properties, certain axis it is going in the opposite direction, particular nodal location, and in the reverse direction for the action material, and that creates a huge amount of stress at those local conditions, local locations. Saving in the deformed shape. Okay, those who are not question. What is this? Okay, sorry. Let me read. If I missed out on anything, okay, that's fine. We conclude in required use. Okay. Typically, if there are cases wherein we want to understand if a glue is enough to withstand these two parts or a kind of weld, then we can see shear stresses, appropriate planar shear stresses, check the values and decide if it is crossing a certain limit or not. And on the other hand, this option of create form body is action. Let me show you where it is. So it could be stress analysis, static analysis, or a thermal stress analysis. You should be able to see this option of create body from deformed shape. Either put it into a part, a new part, sorry, a configuration or a new part. So you can decide what you want to do. Give into it and just accept it. It will get that proper configuration, and the deformations that you are seeing now, those be exported into a new configuration itself. I forgot a bit on this exact location of this capability, but you might want to recheck. But if I remember rightly, this option is present in simulation professional only. Okay, on these topics, biometry will be in the VML format. Huge number of surfaces will be created. Not exactly a good geometry to be utilized, but it can give a good starting point for any further optimization of the design. They can put the deformed geometry, take it to the actual design, check if even with these expansions, it's okay to continue with it. Into the last two chapters on adaptive meshing and bit of theoretical things on meshing, the large displacement option. Questions as of now? Okay, any questions? Let me move into adaptive meshing. Um, Yesterday already discussed about something called as elements, which was more towards the elements that we were using here. In as of now, rather, let me open the appropriate model for this thing, which is present in lesson 13. Okay, is a part? Yes, it's a part. Okay, let me go to the standard meshing. Let me start directly. Let me results with me. You have yes, here. Did I do too many things for the software handler? Looks like. I'll give you more seconds to recover, but in the meanwhile, let me proceed with this. Okay. So a simple model. So yesterday, as we discussed, we have draft quality elements with linear interpolation of results between two end nodes. Then we have high quality elements where a mid-side node, and that helps actually internal to the software. We are actually calculating it in quadratic format, and then we also think of something called polynomial elements or p elements. Okay, these can handle or these have equations all the way from 2 to the polynomial. Now let me go back to this thing. So I used this image yesterday to do what exactly we mean by the size of the element. Okay, so the way we say it is, if this particular tetrahedron element is encompassed by a sphere, then the center of the sphere is telling us the height or the size of the element. Okay, let me go down here. I'll show this options directly in the software. Okay, I think I should not have done that. I should stop it. Okay. Go back desktop, start one more session of SolidWorks. We get a few extra things here. Okay, full results are there and I need not recalculate them. I lost. Okay, fine. Keep them. Okay, properties. Okay, so when we in the case of the study, you will see this option of adaptive. The default is none. That is, no adaptive meshing will be done. This adaptation happens as per the results. Okay, so as per results requirement, the change of mesh happens. First of all, H adaptive options, we have these things. Number one called target accuracy. So vary the accuracy anyway 80 to 100% or 99%. And what is this all about? Typically solve the certain size of element, it comes up with a maximum stress value. Then it will improve the quality of the mesh and then resolve it. On that, we do two different results. It will get the variation of results, or it will get the change the results between these two things. If this result is more than 4%, or we want accuracy of 96% here, so more than 4%, then it will further refine the mesh and try to do one more iteration. And the alignment does not happen all over the model, but happens at a localized condition of the place where the stresses are maximum, or the where it is saying bad results. Okay, and we also have the accuracy bias here. So in this case, this is telling to find the mesh at a location where it is getting bad or where the stresses are more. If you use local or faster, obviously it will do only local refinement, and if you use the global, or if you move slider towards the global, it will try to refine the mesh on complete geometry. And this cannot go infinitely. It loops a certain number of loops only, and we can control it. So here we have 5 loops, the maximum. So it will try 5 different times to find the mesh, and then it can stop. We also like after 5 loops are done, we can check the results. If we are not happy, they can re-trigger the solution. It restart from the location where it has stopped, and we can do five more iterations. There is also an option of mesh coarsening, where the results are not high or the stresses are not high, it actually coarsen the mesh at those different locations. So how it works in this, okay, the way this H adaptive is working, it is actually remeshing the entire geometry. So it will take a huge amount of time to do this activity, and you can imagine the other defects of using this kind of iteration. In that, we have one more option called as P adaptive. Biggest difference over here is we are not remeshing the geometry. The mesh is not recreated, but those appropriate elements, wherever the stresses are high, it is only going to use a higher polynomial. So by default, or as I told you, if it is a high quality mesh, the polynomial is 2. It can actually go on increasing the order up to 5. So it can 3, it goes up to 5 at those elements only. So it is only changing the internal equations of those elements. That is it, nothing much. And these can be driven from any one of these, that is either the total strain energy variation, there is a variation between results, or other things. I may not explain these things in more detail, what exactly is total strain energy or mesh displacement, etc. But these are available in the online help. And this is the second adaptive mesh technique that we have. Now, point from yesterday's discussion on stress singularity, you may have understood that we cannot or we should not other way around. If it is a stress singularity in the model, obviously when we increase the number of elements, it or polynomial, it would diverge, or the results would never converge for a adaptive technique, and we end up seeing an output which says that it has failed to converge, and can go on and on and on. So obviously this is not suited models which are having stress singularity. Second thing, typically assemblies or contact where there is a huge number of contact sets, then again it does not make sense because the number of iterations can be huge. Other, if it is a non-linear, of course the software itself does not give, but it does not make sense because solving one non-linear iteration itself takes a huge time. And go in this way, then it might take comparatively a large amount of time to solve, and again that does not make sense over here. So in these few different points, have a good judgment. It is better to do this mesh convergence manually or on your own. It is an option at the part level wherein we can refine the mesh, understand where we want to have a better mesh and where it is okay to have a worse coarse mesh. Thereon we can give these values manually on one, and then decide and go ahead with it. Okay, I can discuss or explain in H adaptive and P adaptive. Guys, on these topics. It says, can we save the mesh settings from a H or P mesh? No, we cannot save, but what we can do is something different. I can understand what you mean. You want to take the mesh settings and take it to a further model. So good question. My knowledge is no, we cannot. We can just visualize it. We can kind of know the element that it has reached to or the size of element, but from that nothing much can be done with that. It is that. And yeah, I would accept your point. That would be a good option. We'll have to see. Counter to these questions. Okay, good one. As for terminology, why we are upgradable? Okay, how make this look? Okay, why are upgradable elements called P elements? I think this you should have understood now. We explained it. Why is the P conversion process called a P adaptive solution, and what exactly is adaptive mean? Again, you should have understood this. Adaptive in the sense it is adapting as per the concentration. So wherever stresses are more, it is acting over there. Okay. Proceed with the P adaptive. Okay, that's fine. The mesh would not be whatever I've seen as of now, the in commercial uses, of course, theoretically this is discussed a lot. Going to cases, customers might ask you whether you have it or you don't have it. But in terms of commercial applications, I have seen people rarely using it. Live more on their own personal judgment than adaptive technique, because it comes with a huge number of limitations, not on our software but other softwares as well. And other round, if simply it is good for parts, from at the parts level we can understand what's happening, and on we can do meshing on our own. So there is a differentiation also in terms of what the difference between H adaptive and P adaptive. I think it will be okay. That is better. Oh, good question. Okay, fine. About both this chapter of adaptive meshing, and more controversial is this last chapter of large displacement. Now, finally, large displacement is a non-linear condition, and logically I would have expected it to be present in simulation premium only, but we do have it here. And what it can do and what it cannot do is a huge matter of discussion, and frankly does not end. It's a bit of complication. But to put it simply, if you remember yesterday, now there are many different ways in which it is explained. But first and foremost, if you remember what I mentioned yesterday, or the day before yesterday, if the displacement in true scale is visible to your eye, that is visibly seeing a displacement, that means it is not a linear analysis. You need to move into the non-linear analysis. This kind of non-linearity, wherein the displacement is more, it is called as geometric non-linearity. This is more of a geometric non-linearity. And when this comes into picture, there are many different kinds that happen inside the material. One is something called as stress stiffening. That is when the geometry changes, the I would say, how can I say, the ions or the molecules inside the metal rearrange themselves, and the material property changes. It becomes more and more stiffer when it is subjected to such kind of large deformation. That is one difference that happens. Secondly, imagine when the displacements are more, the load direction changes. That's what you are seeing here in the image over here. Compared to K or to A, at C you can see the load direction changes. So for all the analysis wherein we are not selecting this option, we are actually saying that the load direction remains same throughout and not going ahead with it. But if I select this option, the load direction changes as per the direction of the displacement or as per the part moving in a certain direction. Hmm. So setup we are doing that itself. Let me try to go to the setup. We have a setup over here. Where did the large displacement option go? I missed out. I'm too many things. So this option is not selected, okay? And the solution is done. Sort, okay? More sort. That message came, no doubt. Okay, message came. We are actually seeing this plot here. Let me try to take a standard view, and this is how it looks. So, of course, graphics thing, but the forces are not changing the direction. Like it's showing there, that's the reality. It just goes straight. Number, you can just imagine this. This is what's happening. But if the option is selected, large displacement, frankly, we don't have much control on this analysis apart from selecting this option. So typically, if you get that option warning of large displacement, and you think is because there are many other reasons why that warning can come, but it is because of this kind of huge amount of deflection, then you might want to just select this option and solve the setup. You should see a completely different kind of result. And you can see here, while it is solving, it is iterating. That is, it will solve for a certain step. It will basically the matrix will change in these set of iterations, wherein the stiffness of the geometry changes. Now, how much it's change, what is changing, where is changing, frankly, there is no definition, no help, no content on this topic. It's just that it is considering the stiffness change of the geometry because of that thing. Number two, these directions. Now, obviously, when it goes an amount of deflection, the force direction should change. That's what happens. It changes, and then on it again solves. It changes again. It solves, and it gives us a final result, which is actually because it's more realistic than what we saw before. So in this case, we are seeing some visible displacements happening, and we have activated large displacement, and this is the final result. Obviously, it is far different than what you saw here, and with large displacement, it is definitely more accurate than what you saw. But as I told you, this is a non-linear thing. This is a very sensitive topic in terms of what we do here and what we can't do here. Neither do we have too much help or explanation on this. So here it goes. Options on this topic while I quickly scroll through the training manual. If anything important that I have left out. As per the training manual, solid simulation suit computations limited to small displacement analysis only. So this is a fact. It is limited to small displacements only, and are not limited models that experience stresses below material yield strength. Yes, that is also true. I think these two topics are well understood now. Okay, any questions on these topics before I move into the appendix, which is more for I'll show you what the content is, and if I find anything out of the way, then I'll try to explain it. Then without activating mesh coarsening, then which I'm trying to. Do you mean without activating mesh coarsening, the element will be refined only? Activating coarsening can give the most optimum number of elements to use for nonlinear analysis. No, first of all, this mesh coarsening etc. is available, I think, only for static. In nonlinear, you may not be able to see it. It not make sense to use it over there. But around, what happens when more mesh coarsening is used? So let's take an example. I am meshing the geometry in a certain way. Sorry, meshing using the adaptive technique in a certain way. In the second iteration, when it is refining, if mesh coarsening is not selected, it will do only refining at the location where the stresses are more. On the other hand, if it has to be done, if the more mesh coarsening option is selected, it will coarsen the mesh at certain locations, that is where the stresses are not more, and it will refine the mesh only at location where the stresses are more. That's it. So if the mesh coarsening option is selected, it will coarsen the mesh where you don't need good mesh and refine only at that location where it will refine at the location where the stresses are more. In way, in the overall model, the stresses could be or the number of elements will be optimized instead of having huge number of elements. Any questions? Can I mesh from a mesh person to get more optimum number of elements for non? Unfortunately, a similar question was there from David as well, wherein can we take the mesh basically from this H adaptive or P adaptive technique as it is and use it for a non-linear analysis? So I am looking at 2-3 different things. Number one, I create a non-linear simulation. I just copy paste the mesh. You might be knowing you can actually drag and drop the mesh from static analysis to a non-linear analysis. That can be done and that can be used in that. But other options I don't remember or think of any other way. The easiest way would be, yes, drag and just do a additive analysis and drag and drop the mesh from a non-linear. That can be done. I might drag for 10 more minutes than 12 noon. Excuse me for that. Let me check. No, not much content remaining. That's okay. Okay, let me move. Mesh strategies, geometry preparation, mesh defeaturing. This should be okay. Realization we discussed a little bit. Clean up by these topics are useful in terms of cleaning or idealization of the geometry. If all the geometry is imported, sometimes when we import a geometry, it might have some small entities here and there, and that can create problems. So it is more sensitive and useful at those locations only. But other places it's fine. Other way around, if the geometry is created in SolidWorks, typically we are having a clean geometry. Yes, this is important. Let me check. Emerging aspects. Okay. These things which I did not highlight too much, which directly discussed. So first of all, aspect ratio, one of the parameters that we use to check the quality of the elements. Simply speaking, we say it is the ratio of the smallest or the highest length in element to the lowest length, and that's what is shown. But in terms of software, this is what happens. So the black trial is actually the element, and see the repeated fiddle on the entire thing, which is called a large radius, and thereon there is one more circle inside it, which is called a small radius, and this ratio is shown by the software. Actually, now don't imagine it in 2D, imagine it in 3D. It is far more complex. So this is actual calculation that happens inside the software, and that is what is aspect ratio. And can be anything. As you saw yesterday, for accurate results, software says, or the training manual says 50. We go to companies, they say it should be below 20 or below 5 to give accurate results, or they accept results if you have created a mesh which is an aspect ratio of less than 5. And yeah, that's how it goes. And shape, excessive distortion. This is good. So this was a few images in terms of aspect ratio. Yeah, even this way it can be seen as longest normal to the shortest normal. Okay, I think the previous image was more for shell elements. This is for tetrahedrons aspect ratio. But basically, you can directly see the results and do it. Okay, Jacobian check. You can see here. Yesterday I tried my best to draw this particular image. Okay, the edges can get as bad as what is shown in the right side over here, and the side edges can actually intersect each other. Obviously, this is not desirable, and we don't want to be stuck in this condition. So if it is that case, then try to the Jacobian option is going to help you ensure it is all good. And if you observe the Jacobians options over there, you will get Jacobian check for 4, 16 or 29 Gauss points. So as while discussing nodal and elemental stress, I told you about Gaussian points. These exactly they are located somewhere inside the element. Okay. Imagine if you want to check if the Jacobian is good or bad, with more number of points. So assuming if I take only 2 points on this element, that is the end points, it will appears to be good. But if I have more number of points, I can know if element has gone bad in this way. So obviously it can be either at the nodes or it can be at Gaussian points inside, and it can be as high as 29 Gaussian points, and that can help us understand whether the path is going to fail. If the element is not good as per Jacobian check. Okay, discussed yesterday, if I remember rightly, 1 is tending to worse and 0 is tending towards good. Okay, I scroll this, I can see action as well. It says, can adaptive mesh work on shell elements? What about solid assembly? Shell mesh, it does not, and adaptive mesh shell elements. I would frankly not use it, in the sense shell elements are good enough in terms of convergence. We can use different techniques over there. It is comparatively smaller geometry, but no, that is right. Solid assembly. What about solid assembly? No problem, it works. While explaining a few minutes back, I just said we not want to use it because typically as the model size increases, you need more amount of time to solve. Imagine if we give it for adaptive techniques, it might take huge amount of time to solve. Second, as soon as assembly come into picture, and that too realistic assemblies, there are high chances of having singularity, and the software might end up refining the mesh as singularity locations instead of refining at the right location, and that can confuse the software. And hence, I suggest may not be a great idea to use adaptive techniques in assembly. So this should be good. This should be good. This is no big deal. Meshing stages. The diagnostics. I think this I showed a little bit on this topic. Meshing assemblies. Yeah, these are good techniques in terms of you want to find your understanding on ensuring the right geometry for assembly. Using shell elements. Yeah, these are also good. For the hardware corrections for meshing. Direct span, large problem, direct spans, indirect spans, tricky. Choosing it, problem, computer resources, analysis option, element type, properties, that's fine, customer. Okay, reports. I think you guys are all experts in that. This one I used on the first day itself, wherein I told you the location of simulation PDFs, some base user group discussions, knowledge. This is all covered in my first day. Okay, fantastic. This is it. Okay. Looks like we are almost done. This questions on simulation simulation training manual and whatever I covered in these 3 days. Uh, Now, in the next few minutes, I may be on for another 5 minutes. Or you can drop me an email. I believe most of you have received many emails from me, so you should have my email address. If not, it is this. Secondly, as I told you, we are doing this kind of training for the first time. So I was not sure how much time we might need it if I discuss only theory and using the online option. So we are to cover the SolidWorks simulation training manual, which is almost 500 pages. It needs 9 hours at least. That's what we do in these 3 days to cover it with the breaks, etc. So I think this looks good. As of now, I should not hurry up too much, feed too much to you guys. So in these days, this is what I could manage to cover. We can, or the links all have been kept active and open on the decks, so keep them handy with you. Next week, I'll give you an email on this topic, but it will be March 17th to 19th. Again, 9 a.m. to 12 noon. I will finish session professional training manual and motion. Okay, these two I try to get in over there. So I do in 9 hours. Probably I need 3 hours for motion and 6 hours for simulation professional. Frankly, when it comes to simulation professional, it is more of concept. There are 5 to 6 different concepts like frequency buckling, optimization, thermal, etc. So those concepts have to be discussed in those sessions, and doing them in the software is no big deal. Obviously, if you have practiced well and good, but I'll try to cover those different concepts in those 6 hours. Motion, it is more of a concept in understanding redundancies or the way the parts are connected to each other. That's it. Rest of it is very easy. Just low boundary condition, no big deal. But understanding how you integrate and use them is a difficult thing. So, thanks for your time in these days. Hopefully, the sessions were informative. You could ask a lot of things. We will try to catch up in the next week to go with simulation